Sweet history. 8000 BC New Guinea origins. 1500 BC India cultivation. 350 industrial marvel. Sugarcane 15 to 20% sucrose. Harvest mechanical 60 to 100 tons per hour. The journey of every crystal of sugar begins in tropical plantations, where sugarcane, one of the world's most efficient
Mature sugarcane stalks contain up to 15% sucrose by weight, stored in the fibrous stem tissue. Inside each sugarcane stalk, a tough fibrous rind protects the soft pith where sucrose-rich juice.
Modern mechanical harvesters can process 30 to 40 tons of sugarcane per hour, cutting stalks at the base, stripping. Rotating disc cutters slice through sugarcane stalks at ground level. Timing harvest correctly is crucial, as
tractor fans remove leaves and trash while the valuable stalks continue through the harvester. This cleaning reduces the bulk that must be transported and processed at the mill.
chopped cane billets, each about 10-12 inches long, flow continuously into transport trailers.
In some regions, traditional hand cutting with machetes remains common. While labor-intensive, this loaded transport trucks carry fresh cane directly to mills. Speed is essential as sugar content begins declining in
Fresh-cut cane weeps juice from cut surfaces, beginning the sugar loss that makes rapid processing essential. Continuous truck convoys connect fields to mills during the crushing season. Large mills may receive thousands of
cycles. Modern sugar mills are impressive industrial complexes capable of processing 10,000 or more tons of cane.
Every truck is weighed on arrival to track cane deliveries. Payment to growers is based on both weight and sugar content.
Mechanical probes extract core samples from each load for laboratory analysis. Brix measurement indicates sugar content, determining the value of each delivery. Laboratory analysis measures Brix, hull, and fiber content of each delivery. These measurements guide processing parameters and ensure fair payment to growers.
Hydraulic lifts tip entire truck trailers, releasing cascades of fresh cane onto release systems. Fresh sugarcane tumbles onto conveyors that will carry it through the milling process. The race against sugar degradation has officially begun.
Cane yards maintain buffer inventory to ensure continuous mill operation. However, yard time is minimized as
Front-end loaders constantly manage cane yard inventory, maintaining fresh material flow to the crushing equipment while preventing excessive storage time. Continuous conveyors carry cane into the mill at rates exceeding 500 tons per hour. This steady flow.
Washing stations remove field soil and debris from cane stalks. Clean cane improves juice quality and reduces wear on crushing equipment.
Ahead lies the cane preparation area, where powerful equipment will shred the stalks, exposing the sugar-rich.
Clean sugarcane stalks, heavy with accumulated sugar, are ready for the preparation and extraction process that will liberate their sweet treasure.
Quality inspectors monitor incoming cane for excessive trash, damage, or deterioration. Raw material.
The cane preparation building houses the powerful equipment that tears apart sugarcane stalks, preparing them for juicing.
As sugarcane enters the preparation equipment, the transformation from agricultural product to industrial raw material begins.
From tropical field to industrial mill, sugarcane completes its journey in hours. The efficiency of this supply chain, the continuous flow of fresh sugarcane, feeds the mill's insatiable appetite. Processing this agriculture. The cane preparation hall houses some of the most powerful equipment in the mill. Rotating knives and hammer shredders.
Rotating knife sets spin at high speed, their massive blades slicing through the cane bed. These cuts expose
Each pass through the knives reduces cane to smaller pieces. This size reduction dramatically increases the surface area exposed for juice extraction.
Hammer shredders follow the knife sets, their massive rotating hammers pulverizing cane into a fibrous mass. Shredded cane emerges as a fibrous pulp, its cellular structure thoroughly disrupted. This prepared cane flows continuously toward extraction mills. The thorough preparation ensures maximum sugar recovery during the crushing process. The crushing mill tandem consists of multiple heavy roller mills arranged in series. Each mill further compresses The first mill applies enormous pressure through grooved rollers, crushing prepared cane and releasing the first flood of
Raw cane juice streams from the crushing mills, this brown liquid containing 10 to 15% dissolved sucrose along with impurities that must be removed during clarification. Multiple mills in sequence extract progressively more juice from the cane fiber. By the final mill, the fiber has released over... Imbibition adds water between mills to dissolve and extract residual sugar from the fiber. Water washes through the cane. With each crushing, the fiber becomes drier and more compressed. The diminishing juice yield indicates successful extraction of the dissolved sugar. Juice collection systems gather extracted liquid from all mills. This combined juice, called mixed juice,
Exhausted fiber, called bagasse, emerges from the final mill with moisture content around 50%. Bagasse fiber retains substantial energy content despite sugar removal. Most sugar mills burn this byproduct.
Conveyors carry bagasse directly to boilers where it fuels steam generation. A large mill can generate 50 megawatts or more of electricity from this renewable fuel.
Bagasse boilers burn the extracted fiber to generate high-pressure steam. This steam powers turbines for
Raw mixed juice contains dissolved sucrose along with suspended solids, organic acids, and other impurities.
Initial screening removes coarse particles and fiber fragments from the juice. This mechanical clarification precedes the juice weighing and brick measurement track extraction efficiency. These continuous measurements help operators optimize mill settings for maximum sugar recovery. Brix readings on extracted juice typically range from 12 to 18%, indicating the sugar concentration that will be extracted. Juice pumps continuously to clarification. The transformation from turbid brown liquid to clear syrup begins with chemical treatment and settling. Milk of lime adds calcium hydroxide to raise juice pH. This alkaline treatment precipitates impurities and protects sucrose from inversion during heating.
Lime reacts with organic acids and precipitates impurities from the juice. Proper lime dosage is critical. Too little. Ahead lies the clarification station, where heat and chemistry combine to remove impurities.
The juice heaters raise temperature to near boiling, accelerating chemical reactions and reducing viscosity for settling. Heat also destroys enzymes that would otherwise degrade. Temperature control during clarification balances impurity removal against rust protection. The clarification station removes impurities through chemical treatment and gravity settling. Continuous clarifiers allow impurities to settle as flocculated mud while clear juice rises to overflow. Residence time of 2 to 3 hours ensures thorough settling.
Flocculation aggregates fine particles into larger masses that settle more quickly. Polymer flocculants.
Clear juice overflows from the clarifier top, leaving settled impurities behind. This clarified juice shows dramatically improved. Mud underflow removes settled impurities from the clarifier bottom. This thick sludge contains residual sugar that will be recovered through filtration. Rotary vacuum filters extract residual juice from clarifier mud. The recovered liquid returns to processing. Filter mud makes excellent agricultural fertilizer, returning nutrients to cane fields. This byproduct rift. Clarified juice accumulates in storage tanks, maintaining steady feed to the evaporators. This clear liquid still... The transformation from turbid raw juice to clear clarified juice demonstrates successful impurity removal. The evaporator station concentrates clarified juice by removing water. Multiple effect evaporators use steam energy.
First effect receives live steam from the boilers, heating juice to boiling. The vapor released from boiling juice provides heat for subsequent effects.
Inside the evaporator, clarified juice boils vigorously under reduced pressure. Lower pressure reduces vapor from each effect provides heat for the next and temperature decreasing through the series. This is
4 or 5 evaporator effects typically operate in series. This arrangement can evaporate 4 pounds of water for every pound of steam consumed.
The final effect operates under high vacuum, allowing juice to boil at temperatures low enough to prevent sucrose damage.
Condensate from evaporators provides clean hot water for process use. This recovered water preheats incoming juice and provides imbibition water for the mills.
Concentrated syrup exits the final evaporator at 60 to 65% solids. a dramatic increase from the 12.
Concentrated syrup displays dramatically increased viscosity compared to clarified juice. The golden brown color intensifies as water removal concentrates remaining impurities. Brix measurement confirms syrup concentration before crystallization. Proper concentration is critical for efficient crystal formation in the vacuum pans.
Syrup storage tanks provide buffer capacity between continuous evaporation and batch crystallization. It ensures vacuum pans receive consistent feed material.
Regular sampling monitors syrup quality, including purity and color. These parameters affect crystal quality and determine the optimal crystallization approach. Regular cleaning removes scale deposits that reduce heat transfer efficiency. Proper maintenance ensures evaporators perform at design capacity throughout the crushing season.
Operators monitor evaporation from central control rooms, maintaining proper levels, temperatures, and concentration. Modern control systems display real-time evaporator performance. Automated controls maintain optimal conditions, while
Steam economy measures how efficiently evaporators use energy. Well-operated multiple effect systems achieve economies of 4 to 1 or better.
ahead lies the vacuum pan station, where concentrated syrup transforms into sugar crystals. This batch process, called properly concentrated syrup containing 60 to 65% dissolved solids, is ready for the crystallization process that will
Syrup transfers to vacuum pans, where controlled crystallization will occur. The transformation from liquid to crystal represents the heart of sugar manufacturing. Multiple vacuum pans operate simultaneously, each at different stages of the crystallization cycle. The vacuum pan station is where sugar crystals are born. These large vessels, operating under vacuum at
Vacuum pans are batch crystallizers holding 40 to 60 tons of mass acute. Under vacuum, syrup boils at reduced temperature.
Crystallization begins with seeding, introducing small crystal nuclei into supersaturated syrup. These seeds provide seed slurry contains microscopic crystal nuclei suspended in alcohol. Proper seeding density determines final crystal size and uniformity.
Experienced sugar boilers sample crystallizing massacete with proof sticks. The appearance, consistency, and crystal development guide feeding and concentration decisions.
Proof stick samples reveal crystal development. Skilled operators recognize optimal crystal size and mother liquor consistency, adjusting the process accordingly.
As crystals grow, operators add fresh syrup to maintain supersaturation. This feeding provides the dissolved.
Steam heating through internal calandria tubes provides the energy for water evaporation. Controlled heating maintains the supersaturation that drives crystal growth. Calandria tubes provide the heat exchange surface where boiling occurs. Syrup circulates past these heated surfaces, evaporating water and concentrating the sugar solution.
Vacuum systems maintain pressures around 25 inches of mercury, reducing boiling temperature to approximately 150.
Condensers receive vapor from the vacuum pans, cooling it back to liquid. This condensate joins the recovered water used throughout the mill.
Under magnification, growing sugar crystals display their characteristic monoclinic structure. As crystallization progresses, the massacroid thickens dramatically. The pan reaches heavy when crystals achieve target size. Tightening further concentrates the massacete without additional feeding. This final step maximizes crystal content and prepares for discharge. Finished massacete shows well-developed crystals surrounded by mother liquor. This mixture, called a strike, is ready for discharge and centrifugal separation. Pan discharge releases the completed strike through large valves. The heavy massacete flows by gravity to receive tanks or directly to centrifugal separation. Crystallizers provide additional residence time for crystal exhaustion. Slow cooling promotes additional crystal growth from the supersaturated mother liquor.
Slow stirring in crystallizers prevents crystal settling while promoting uniform cooling. This additional growth improves overall sugar recovery. Sugar mills typically operate three-stage crystallization. A sugar provides the highest quality, while B is. Multiple vacuum pans operate continuously, each at different stages of crystallization. This orchestration maintains.
Despite modern automation, experienced pan operators remain essential. Their visual assessment and manual adjustment.
Modern pan control systems automate much of the crystallization process. Sensors monitor supersaturation.
Ahead lies the centrifugal station, where spinning baskets separate crystal sugar from mother liquor. This mechanical crystallized massacete, containing 40 to 50% crystal sugar surrounded by molasses, awaits centrifugal separation. Massacete transfers to centrifugal feed systems that distribute material evenly to the spinning machines. Even distribution ensures efficient separation.
Arrays of centrifugal machines operate continuously, each spinning at high speed to separate sugar crystals from surrounding molasses.
Centrifugal baskets contain fine perforations that allow molasses to pass while retaining sugar crystals. The basket spins at speeds up to
As the basket spins up to speed with loaded massicute, centrifugal force presses the mixture against the perforated wall. Molasses flies from the spinning basket, collecting in surrounding channels for recovery. This separation happens rapidly, typically completing within 2 to 3 minutes per cycle.
The centrifugal station separates crystal sugar from molasses through high-speed spinning. Both batch and control. Batch centrifugals complete separation cycles in 2 to 3 minutes. The spinning gradually slows as molasses is removed.
water washing sprays clean residual molasses from the sugar crystal surface. This washing improves color and quality of the separated sugar.
Steam application provides final drying and polishing of the sugar crystals. The hot steam evaporates surface moisture while improving crystal appearance.
As the centrifugal slows, a plow scrapes sugar from the basket wall. The separated crystals fall to
Raw sugar crystals display characteristic golden brown color from residual molasses. This color will be removed in refinery processing for white sugar production.
Continuous centrifuges provide steady sugar output, handling lower-grade massicutes. These machines operate without batch cycling, maintaining constant production.
Separated molasses collect for further processing or sale. This thick, dark syrup contains significant residual sugar and valuable minerals and flavor compounds.
A molasses from first crystallization returns to the process for additional sugar recovery. Multiple crystallization steps. Final molasses, called blackstrap, contains sugar that cannot be economically crystallized.
Conveyors carry separated sugar crystals to drying operations. The still warm sugar must be cooled and dried before storage to prevent caking. Rotary dryers and coolers reduce sugar moisture content and temperature. Proper drying prevents caking and microbial growth during storage.
Dried sugar crystals meet moisture specifications for storage stability. The characteristic sparkle of raw sugar crystals indicates proper drying.
Greening separates sugar by crystal size. Different grades meet various industrial specifications and customer requirements. Bulk storage warehouses hold raw sugar production for shipping. Mountains of golden crystals await transport to refineries worldwide. Bulk raw sugar displays the golden brown color that distinguishes it from refined white sugar. This color comes from molasses film.
Bagging operations package raw sugar for commercial customers. These bags ship to food manufacturers or refineries for further processing.
Laboratory testing verifies raw sugar quality, including pall, purity, color, and moisture content. Polarimetry measures to determine sucrose purity.
Some mills include refinery operations that convert raw sugar to white refined product. This additional
Refinery processing begins by melting raw sugar in hot water. This dissolved sugar undergoes additional clarification and crystallization for white sugar production. Activated carbon filtration removes color bodies from dissolved sugar. This treatment produces the crystal clear liquor needed for white sugar crystallization.
Refined sugar crystallization produces the pure white crystals, the fine white crystal.
White refined sugar emerges brilliant white from centrifugation. This product meets the color and purity standards for direct food use.
The contrast between raw and refined sugar illustrates the additional processing that removes color. Both contain nearly
Stations. The Quality Control Laboratory verifies every aspect of sugar production. Comprehensive testing ensures product.
Polarimetric analysis measures sucrose content with extreme precision. This measurement determines commercial value and guides process optimization.
Color measurement in ICUMSA units quantifies sugar whiteness. White refined sugar typically...
Moisture analysis ensures sugar meets storage stability requirements. Excessive moisture promotes caking and microbial growth during storage.
Microbiological testing verifies sugar safety for food use. Despite high purity, proper testing ensures absence of harmful organisms. Crystal size analysis ensures sugar meets specifications for specific applications. Different food products require different crystal sizes.
Quality teams continuously analyze production data, identifying trends and improvement opportunities. This ongoing effort maintains consistent product.
The packaging hall fills consumer and commercial containers. Multiple lines package different product types and sizes simultaneously.
Automated filling ensures precise weights in every package. Quality systems verify fill weights meet declared quantities. Sealing and date coding complete consumer packages. Batch traceability enables quality management and supports any investigations needed.
Palletizing prepares finished sugar for distribution. These packages will reach grocery stores, food manufacturers, and food service operations worldwide.
Modern sugar mills produce diverse products, including granulated, powdered, and specialty sugars. From the shipping dock, sugar travels to customers worldwide. Bulk shipments feed refineries and food
Bulk rail shipments transport raw sugar to coastal ports and refineries. Rail provides economical transport for the massive volumes modern mills produce. Bulk vessels carry raw sugar to refineries worldwide. International sugar trade connects tropical producing regions with consuming countries globally.
Packaged sugar inventory awaits distribution to retailers. These familiar packages will appear on grocery shelves within weeks of production.
On grocery shelves, sugar completes its journey to consumers. The crystals that grew in tropical fields now await kitchens everywhere.
In kitchens worldwide, sugar sweetens countless foods and beverages. This natural product, concentrated from
Pure sugar crystals represent the successful concentration of sunlight captured by sugarcane. Each crystal contains the energy harvested from tropical fields.
Inside a modern cane sugar factory, an agricultural crop transforms into one of the world's most important